we are looking at ultimately trying to figure out the connection between kinetic energy and temperature. But first we need to figure out what is the pressure that a gas exerts on an object. So imagine that I have some sort of rectangular solid, some sort of box. And this side right here has some area A, and this length right here, we're not going to do anything with, but just for the sake of a picture, L. And so the volume, the total volume is L times A. I want to imagine, as we're thinking about pressure, pressure is caused by particles bouncing up against the wall, so we need to take a look at that. So I'm going to take this side right here. I'm going to call that the x direction. And I have some particle that's heading straight towards it at some speed v sub x. So if I have some particle of mass m heading to the wall, it has an initial momentum heading in this direction, heading to the right. We'll make to the right positive of mvx, and then it's going to rebound. Now, at this scale, perfectly elastic collision is perfectly reasonable when you're dealing with particles. So we are dealing with a perfectly elastic collision. It will maintain all of its elasticity, and so it'll bounce back with some speed vx to the left, and so it will have a momentum of mvx heading to the left. If we look at the impulse, J being impulse, that the wall exerts on the particle, that's the impulse, on particle from wall. That should be equal to, well, that's the impulse is equal to the change in momentum. It's also equal to the average force times time, which equals, for a calculus, force times f dt, from some initial time to some final time. I want to look at the momentum aspect of it. It's final momentum minus initial momentum, which in our case right here, for the particle, since this is the impulse, it's the impulse on the particle from the wall. That's going to be negative mvx, because I said to the right was positive, minus mvx, which is negative 2 mvx. This is the impulse on the particle from the wall. So since that's equal to the average force times time, the average force on the particle is negative 2 mvx delta t, or this is on the particle from the wall, or the average force on the wall from the particle is positive 2 mvx over delta t. Now that's just a single particle, so if I have n particles in the box, so let capital N be number of particles in the box, let n sub col, this is the number of particles which collide with the wall. And so the average force, which I can also write in this form right here, this is in physics, this is the more traditional form of writing average, is going to be that number right there times the number that actually collide. So this is 2 number of collisions, mvx over delta t. Now we can narrow this down a little bit. If I think about this, so I'm sort of looking at an overhead view of the box. So this is my wall right here. Within this time t, moving at speed vx, only particles that are within vx delta t can actually hit the wall. So the number that can collide has got to be somehow proportional to that versus the overall volume. So the volume of possible collisions has to be, well, I basically have just this fraction right here. I'm looking at this small little bit right there. This is Vx delta t times the area. And so that's the volume of possible collisions. If the particles are evenly distributed throughout the box, then we can set up a ratio that the number of particles in the collision as a fraction of the total number of particles should be proportional to basically the volume of this area, which we established was Vx delta TA, over the total volume, which I'll just use as that. And recognize that even though you have a particle in the box, right in this part of the box, not all of them are actually heading towards that wall, and so statistically only half of them would have any component in that direction, and so we throw an extra half in there. We will narrow that down a little bit more coming up, but we have that relationship there. So we have the number of collisions, therefore, would be Vx delta TA times N over 2 times the volume. And so we can substitute that in for the number of collisions. This would be equal to 2 Vx delta TAN over 2V. So that's the 2 there, and then that is number of collisions times mVx over delta T. Delta T cancels out. And what you end up with is the average force being, oh, the 2's cancel out. A N mVx squared over the volume. And that's what we'll pick up on the next sheet. Now we can generalize this slightly because we've sort of been working under the assumption that Vx is the same for everything, that everything's traveling the same speed, and that's really not true. So we can generalize it by just taking the average value of Vx squared. Now recognize, though, adding a little bit more reality to it, the fact that particles are traveling in every direction. The RMS value, the root mean square value, is you take the values you're trying to find the average of, square it, find the average, and take the square root. And V squared, since we have working in 3 dimensions, is Vx squared plus Vy squared plus Vz squared. So the average value of V squared should be the average value of Vx squared plus the average value of Vy squared plus the average value of Vz squared. And since if we're talking about a gas or something like that, particles are moving in every direction, and there's no reason why the average value should be any different in one direction than another. So all those are basically the same, so that should just basically be 3 times the average value of Vx squared. So Vx squared should be 1/3 of V squared. VRMS squared, which is equal to the average value of V squared, which is 3 times Vx squared. I know it sort of went in a circle right there. So Vx squared, average value of Vx squared, should be 1/3 of VRMS squared. So now plugging back into here, we have N over V times AM 1/3 VRMS squared. So with the average value of Vx squared being 1/3 of the RMS squared value, we can now come back up here, and the average value of the force, no longer just in the x direction, is going to be equal to 1/3 particle density AM VRMS squared. And if we divide by the area here, so we have this average force per area being 1/3 particle density times mVRMS squared. This is the pressure. And that will lead into what we do next. In a previous video, we found that the pressure that a gas exerts on the side of a container is equal to 1/3 times the particle density mVRMS squared. Now we know that kinetic energy is 1/2 mv squared. And so the average kinetic energy, so it's a little bit of a hand wave there, is equal to mv rms squared. We can now express this in terms of kinetic energy. So I have mv rms squared is equal to 2 times the average kinetic energy. Pop that into here. And so we now have the pressure equal to 2/3 times the particle density, number of particles over the volume, times the average kinetic energy, the 2 popping out here. Multiply both sides by the volume, so we have PV is equal to 2/3 times the number of particles times the average kinetic energy. So for those of you who have dealt with chemistry before at so many levels, you might be familiar with the PV aspect of it. This is the ideal gas law. PV is equal to nRT. N is the number of moles. Now this might bring back some shudders for some of you, but this is the number of moles. A mole, first off, so little n is the number of moles. And a mole is just a number. A mole is 6.02 times 10 to the 23rd. Just like a dozen is 12, score is 20, a mole is, and that should be 2 words there, a mole, is 6.02 times 10 to the 23rd. It's also known as Avogadro's number. Now the ideal gas law can be expressed one other way. Instead of in terms of number of moles, it can be expressed in number of particles. So that's also N times Kb times T, where this is known as Boltzmann's constant. And so we have this 2/3 times the number of particles times the average kinetic energy is equal to the number of particles times Boltzmann's constant times the temperature. Number of particles cancels out. And what we are now left with is a relationship between kinetic energy and temperature. So the average kinetic energy of a gas is equal to 3/2 times Boltzmann's constant times the temperature. And that is the relationship between average kinetic energy and temperature.